Right. Sorry, I was muted for a while there, but okay. Good morning again, everybody. So last time we continued our discussion about sequences, and we focused more on determining when a sequence is convergent or not. And we said that a sequence will converge if you can find the limit as the nth term, which we usually write as an, approaches a certain finite number, right? Or if the limit of an as n approaches to infinity exists and is finite, right? So we have developed several methods for that. And then let me just answer Taylor's problem here about finding the limit. So, and this one is interesting. Thank you for setting it in, Taylor. I'm not sure if we already saw this sequence last time, but anyway, let me begin here. Let's call it example 14. So here the sequence given is the sequence 3 plus -1 to the power n. Now, if you look at it, we will have, all right, well, it would be a little difficult to find the limit analytically. So we'll have 3 plus -1 to the n. Actually, it's not that hard. So you take the limit as n approaches infinity. And then you see that this is, okay, the first term goes to 3 because that's a constant. But what happens to -1 to the power n as n becomes very, very large? Well, this is an example of a non-indeterminate form, all right? Again, this is not indeterminate because the base is exactly equal to -1. Right? Because remember, we have the indeterminate form 1 raised to infinity from Cal 1, and I think one example from last time. But this is not actually 1 raised to infinity in form of a limit. It's something close to 1 raised to infinity. And that's where the indeterminacy occurs. So if you have something close to 1 raised to something becoming very, very large, that's indeterminate. But in this case, this is not an indeterminate form because the base here is not something approaching -1, but is exactly equal to -1. So you might think of it as -1 raised to the infinity, but the base is an exact 1. So basically this guy is equal to what? Is equal to -1 for odd ends, and it is +1 for even ends. But essentially, what we see here is that it will just oscillate between -1 and 1, right? So that means the limit doesn't exist, not because it is indeterminate, but we see that the limit will not exist because its value will just alternate between -1 and 1. So actually here I can say that the limit doesn't exist because -1 to the power n simply oscillates between -1 and 1. And in the long run, when n becomes large, we don't know what will happen, or there's no certainty that -1 to the power n will go to either -1 or 1 because they will just keep on alternating, right? So, or another way of looking at it, rather than looking at the limit and doing this analysis, is just to list down the first few elements of your series, of your sequence. So when n is equal to 1, we'll have 2, right? And then when n is equal to 2, we get 4. When n is equal to 3, we get 2. When n is equal to 4, we get 4, and so on. And you see the pattern here. The terms of the sequence will just alternate between a 2 and a 4. And in the long run, we don't know what will happen to this. Will it go to 2? Will it go to 4? Actually, it will not go to either of them because they will keep on alternating. So definitely this is divergent because the values will just alternate between 2 and 4, right? So this is your first solution, and this is an alternative one. So alternatively, this would be true. Yes, Daryl, that's exactly what I said in the first in the second solution, which turned out to be the first thing I wrote here. But essentially, that's correct because remember the limit of a sequence is the number to which the terms in the sequence approach towards the end of the list. But here we don't know whether the terms will go to 4 or will go to 2 because they will keep on alternating. So there is no single value to which the ANs will approach when n becomes very, very large. So you have two reasons for that. You can choose between analyzing the first few terms of the sequence and try to discern the pattern, or do a limiting argument. All right. Okay. Is that okay, Taylor? Does that make sense? Yeah, just let me know if you have follow-up questions on that. Okay, great. Now let me go to Maria's question. She sent a question about determining whether the sequence is monotone or not. So when we say it's monotone, yeah, just send it, Taylor. A sequence is monotonic or is a monotone if it is either increasing or decreasing. And being increasing or decreasing is a big thing to ask because um, when we say that the sequence is increasing, if an is always smaller than a sub n plus 1 for all n. So you see how restrictive this condition is. It should be increasing if a certain term is always smaller than, actually you can say smaller than or equal to the next term. So basically, if you look at the terms in your sequence, they will keep on increasing. If you find two consecutive terms in the sequence, that the first one is larger than the second one, then automatically it is not increasing anymore. So it should be increasing for all values of n. So it's a very big thing to ask. It's easier to disprove that a sequence is not increasing by providing a counterexample. An n term that is larger than an n plus 1 term. But saying that it is increasing is a big thing to ask. So let me see Maria's question here. Okay, so there are several ways on how to check whether a function is increasing or decreasing. Now, of course, we say it's increasing if this is true. Similarly, let me just complete the thought here. A sequence is decreasing if an is larger than or equal to a sub n plus 1 for all n. All right. So the question here is, okay, so for the following sequences, determine if they are monotonic. Okay, so let's restart our numbering here. Let's start with problem 1, Maria's question. She was given the sequence n plus 4 over n plus 19. Now the thing here is the numerator increases, right? And the denominator is also increasing. So the thing here is that we don't know if it will always be increasing or not, because the thing is, if you see something that is two consecutive terms that are not in order, then it is not monotonic anymore. So probably I can suggest you start with probably listing the first few elements and see if you can get the pattern. Though I doubt that that would be easier, or actually I'm not sure, n plus 14 rather. So, but we know that this will go to 1, right? The limit is 1, but we don't know if it's increasing or decreasing. Well, let's look at the first few terms. When n is equal to 1, so we get 15 over 20. And then if n is equal to 2, we get 16 over 21. Then we get 17 over 22. And so on. The next one would be, probably let's try the next one. 18 over 23, and so on. Now, with without the aid of a calculator, it's not easy to determine if the first few terms are increasing or not. But I say this one is what? 15 over 20 is 0.75 exactly. I'm using a calculator here. I'm cheating a bit to see if, yeah, then 16 divided by 21, that's about 0.76. 17 over 22 is about 0.7727. And then 18 over 23 is about 0.7826, and so on. So it seems that the trend here is that it seems that the sequence is monotonic increasing, because at least if we're looking at the first four terms, then it suggests that the sequence is increasing. But that's not a definitive answer, because we don't know, because probably at the tail end of the sequence, there might be one term that would be smaller than the next term, or that would be larger than the next term. Because again, being monotonic increasing is a big thing to ask. We should know for certain that that will be true for any n. So how do we do this? There are several options. Let me think a little bit here. What would be the easiest one? Well, let's try if taking the derivative will be good. So remember, one thing that we use from Cal1 to check whether a sequence is if a function is increasing or decreasing is to look at the derivative, right? So here, let's consider the function f defined by x plus 14 over x plus 19, right? So it's a real valued function, but actually I'll just be interested when x is a positive integer. But I need to analyze the real valued counterpart of the sequence n plus 14 over n plus 19 to get the derivative, because derivatives are not defined for sequences, right? So here, if I take the derivative, I'll see that that would be equal to x plus 19 squared. Remember the quotient rule. So this would be low derivative of the high minus high derivative of the low function, right? And if you simplify this, this would be 0, 5 over x plus 19 squared, right? And what can you say about 5 over x plus 19 quantity squared? This would be greater than 0 for any x, right? And the statement that this is positive for any x mean that this is also true for any n greater than or equal to 1. Sorry, for any, let's say for any integer x greater than or equal to 1. So that means, if you remember, when the derivative is positive, that means that the function is increasing. So we can say that f is increasing on its domain, right? Okay. So it is increasing in its domain. So that means the sequence that rides on this real valued function is also increasing. So you can say, thus, the sequence is also increasing. So this is one technique that you can do. Look at the derivative and see if it is always positive or always negative for any integer greater than or equal to 1. So here we got a nice function here. And then we got, we saw that the derivative is positive, implying that the function over all the real numbers except negative 19 would be increasing. So that means the sequence that rides this function f is also increasing. Yeah, I'm not familiar with that formula and for what it is used. 1n plus 1 over n raised to the b to the n. I guess that's for finding the limit as n approaches infinity of an indeterminate form 1 plus 1 raised to infinity. So that's the shortcut that we used, yeah. But I don't think you can use that for checking whether it's monotonic increasing or decreasing. So at least now we have one method. Look at the derivative and see if it is always positive or always negative, at least for integers greater than or equal to 1, right? So you're lucky if the function is nice and you can conclude that it is greater than or equal to 0, okay? That's for Taylor's question. Yeah. Okay. Yeah, sure. I'll go over that in a while. But okay, is this first method clear? Another thing you can do in determining whether a sequence is monotonic increasing or not is to look at the ratio between two consecutive terms. So here, let's say my sequence is an, where an is equal to 2 to the n over n squared, right? So the numerator increases, the denominator also increases, so I don't know what happens. Will the fraction get bigger and bigger, or will it get smaller and smaller, right? So what I can do here, since I see that both numerator and denominators are power, I will try looking at the ratio of an plus 1 and an and see which if that is greater than 1 or less than 1. So what I'm trying to say here is, okay, I'll take a look at an plus 1 all over an, right? So a sub n plus 1 is simply replacing all n's I see in an by n plus 1. So every n here will be replaced by n plus 1. So I'll have 2 to the n plus, oops, let me make it smaller. 2 to the n plus 1 all over n plus 1 quantity squared. All over a sub n is simply 2 to the n over n squared. Then let's simplify. This would be 2 to the n plus 1 all over n plus 1 squared times n squared over 2 to the n. Then further carry on with the simplification. We get 2n squared over n plus 1 quantity squared. Not the result I'm looking for, but let's see. Oh, which one do you think is larger? 2 times n squared or n plus 1 quantity squared? Probably it's not the example I'm looking for, because if I will expand the denominator, I'll get n squared plus 2n plus 1. And do I know which one is always greater? Okay, let's see. If n is equal to 1, then the numerator, let me just try it here. I'll have 2 over 3. And then when n is equal to 2, I'll get 4, I'll get 8 over 4 plus 4 plus 1. So that's going to be 8 over 9. Yeah, that's still less than 1. When n is equal to 3, I'll get 9 times 2, that's 18 over 9 plus 6 plus 1, so that's going to be 18 over 26. Now hold on, when n is equal to 1, I mean here, you mean here, so I'll get what, 2 over, yeah, I'm plugging in 1 here, so I'll get 2, and then 1 plus 2, yeah, oh, so I forgot that too, so this would be n equals 1, 1 plus 2 plus 1, so this would be 4. Should it be 1/2? Uh-huh. Yeah, here it looks like that the numerator is always less than the denominator. But I think that will not be true for bigger values of n, if I'm not mistaken. Actually, this is not the example I'm looking for. So because here it's not clear whether the numerator is always smaller than the numerator. Unless I'm missing something here. Let me see. I cancel things. And then I get 2n squared on top. Yeah. Is it uh is it clear that the denominator will always be larger than the numerator? Because
Wait,
here
I have a question.
Mhm.
Okay, so when you're looking at this question, can't we say that 2n is an exponential and n squared is a polynomial, and then exponential grows faster than the polynomial?
Yeah, you can reason that out. So that means in the long run, the numerator will grow a lot faster
Right.
than the denominator. But that's in the long run. We're sure about that in the long run. But when you say increasing or decreasing, it should be true for any n, big n's, small n's, and so on. That's why I'm just a bit hesitant to conclude right away that it is increasing based on the argument that 2n becomes larger faster than n squared, because that is true in the long run. But for smaller n's, will that also be true? Maybe this is easier than what I tried to do. What will happen when n? Let's try to list the first few terms. I thought this is the example I I answered in one of the tutorials where an plus 1 over an gave me a nice expression. But anyway, let's try to list down the elements. Let's see if the pattern shows here. So if n is equal to 1, we get 2. If n is equal to 2, we get 4 over 4, which is 1. If n is 3, we'll get 8 over 9. And then if n is 4, so we'll get 16 over 16. Did I do the substitutions correctly? So guys, it's already Friday, so kindly check my solution here. Oh, this should be 1. Yeah. Are these the first few terms at least? 2, 1, 8 over 9. So the third term, I plug in n equals 3, numerator becomes 8, denominator is 3 squared, so 9. Okay, so it's easier than I expected because here you see that the first if you look at the first two terms, it seems it's gonna be decreasing, right? But after the second term, it decreased to 8 over 9 because 8 over 9 is less than 1. But again, it started increasing to 1, so that means it's not monotonic. So yeah, that's why you need to be careful applying asymptotics, because the long-term behavior of the exponential and the polynomial is, as Arsalan suggested, numerator becomes large faster than the denominator, but that's true for large n's, or as n grows large. Being increasing or decreasing entails an analysis of the entire sequence, be it for small n's or for large n's. And true enough, we see that when n is equal to 1 and n equal to 2, we see a decreasing trend, at least actually until the third term. But starting from the fourth term, it will start increasing. So yeah. So that's why, okay, let me revise my suggestion here. Try to look at the first few terms first and see if you can see a counterexample or if you can discern the pattern. Okay? All right, does that make sense? Yeah, I was thinking, what was that nice question I answered last time? Yeah. Okay. Yeah, so here are some techniques. So maybe I should summarize it here. To check monotonicity, right? The first thing you can try is look at the first few terms. Because you can see a pattern or a counterexample may emerge. Like in this example that we have, if I just look at the first four terms, I will see a counterexample because it's easier to show a counterexample because all you need to do is to look at some terms that there's an increasing behavior and then a couple of terms that has a decreasing behavior in the same sequence that will make it non-monotonic or non-increasing or non-decreasing. But if that fails, then you can look at f prime and see if it's positive or negative. For x is greater than or equal to 1. If the derivative of the real valued counterpart of your sequence is positive, for all x's greater than or equal to 1, then it is increasing. Then if the real valued counterpart of your sequence is always negative for x greater than or equal to 1, then that means the given sequence is decreasing. All right. So just borrowing some concepts from Cal 1. The third test is look at a sub n plus 1 over an. If you feel that some things will cancel out nicely. If this is less than 1, then um, a simple analysis of terms here can tell us if it's increasing or decreasing, right? Because depending on the sign of an, you can say if the ratio is less than 1, then either a sub n plus 1 is smaller than an, or an plus 1 is greater than an. This happens when an is, the second case happens when an is negative. I forgot to be careful about that because I need to flip the signs, right? So, but basically, once you know that this is true, the ratio is less than 1, then you can conclude if it's increasing or decreasing. The same thing if you can show that the ratio is greater than 1. So all you need to do is to take the ratio of two consecutive terms and compare it with 1. Then you can do the appropriate analysis after that to see if an plus 1 is less than an or is an plus 1 greater than an for any n. And the other thing that you can try is look at an plus 1 minus an and compare it with 0. Because if the first case is true, that will imply that an plus 1 is greater than an. So you can conclude that it is increasing. If the second case is true, then you can conclude that it is decreasing. Okay, so these are 4 things that you can do to determine whether a sequence is increasing or not. All right, I hope this will help you with some of those quiz problems asking you for the monotonicity of certain sequences. Now, the thing is that it depends which of these 3 methods is easier or is easiest to use for a particular sequence. It actually depends on how the sequence looks like. Personally, I start with this one. Look at the derivative and see if it's good. Otherwise, I look at the quotient or I look at the difference. So there's no hard and fast rule. Well, Arsalan, I don't know. Yeah, looking at the topics, if you will just read the textbook, it seems that this chapter is very easy, right? But in practice, it is not because you can encounter some sequences that are very unsuspectingly easy, but when you try to dig in, you'll see some complications and so on. Yeah, I also think it's easy. That's why I forgot to talk about uh, monotonicity, but I encountered several students asking for help about determining whether a sequence is increasing or not. But if you have further questions, just let me know. Yeah. But actually, I received an email from Dr. Almus earlier today that that you guys generally did well in test three, but we should help you more with a lot of example about series, especially when we start next meeting with series or today with series or test for convergence of series, because she thinks it's harder for most students um, to answer test four problems than test three. I don't know, but Herson is right. It's from person to person. Personally, I hated series when I was an undergrad because I'm very poor at memorization. But now I find it easier because I know the reasons behind the tests. So basically, I'm not memorizing the tests, but I'm looking at why those tests work, and now I can remember whether that test the conclusion of the test will tell me if it's convergent or not. But we'll go to that later. All right. So before I wrap up our discussion on sequences, let me go back to Taylor's second question. Maybe I'll insert that here. Let me see if I can insert that here. Yeah, let me insert a page here. Yeah, and then put this down. Okay, so Taylor's question is about the convergence of this sequence. AN is equal to 1 plus 1 over n raised to 11 over 2n. Now, okay. So the thing here is you can do a long solution to this if you don't remember the formulas, which I will use because I think I answered a similar problem last time using Lhopitals rule with the e to the something at the end. So you can go back to the video last Wednesday to see the long solution. But I'll try to use the formula Dr. Almus showed you in the lecture, which Maria and her son provided in the chat. Because here, ideally, what you'll do is to take the limit of an raised to 11 over 2n as n goes to infinity, right? And then you'll say that, okay, I'll transform it to its real valued counterpart so that I can use L'Hopital's rule on how to solve this problem, all right? Now, yeah, let me see. What is that formula supposed to tell us? Yeah, are you sure, Herson, the formula is this? Let me just try to translate what you wrote in the chat. I'm not sure about the subscripts n inside this. Maria, I'm referring to this one instead. Is this the formula that you said you don't know how to apply? Herson, is this correct? You know me, I'm very poor at memorization, so yeah. Because for problems like this, I'll go ahead and solve this using L'Hopital's rule. Okay, there you go. Thank you. Okay, I see. So let me just write that down here. You know what? Until now, if my teacher will tell me to know this as a fact, I'll just ignore her because I hate memorization that much. But anyway, so here's a formula that was given in your class as n goes to infinity of b times n. Okay, so you compare it with this with the given term here. So if you compare this with this one, you can conclude that here a is equal to 1 because you have this, right? Oh, it's perfectly fine because I have the n there. I have the 1 in front. And then I have the n here and the n there. So that means b is 11 halves, right? So that means the limit here is equal to e to the ab. Oh, and it's that easy. So you don't even need to transform it into a real valued function because the formula gives us the limit right away. So here, I'll just use this formula. I'll have e raised to a, but we already knew that a is equal to 1 times b, and b is 11 halves. So there we go. The sequence is 11. The limit of the sequence is e raised to 11 over 2. Okay, that's quite easy. Though honestly, I won't bother memorizing this formula. I'll go with Lhopitals Rule. That's how much I hate memorization. But if you guys are good at it, then it would be very advantageous if you can memorize the formula and then just apply it. Okay. Okay. Is this good, Taylor? So any other question from anybody about sequences? Probably we can start with series. Okay, there are no reactions in the chat, so okay, so let's try going on to worksheet 15, which is basically about series. I guess you had some basic theorem about series on how to determine whether they converge or not. But let's see. Oh, this is a math joke that I hope you now can get. So here, an infinite number of mathematicians walk into a bar, and then the first one orders a beer. The second one says, okay, I'm going to order half of what the previous person ordered. Then the third one says, okay, I'm going to order 1/4, which is half of what the previous person ordered. Then you imagine the fourth one will say, I'll take 1/2 of what the previous person did order, so he will take what? He'll take 1/8 and so on. And then the bartender got pissed, and he just took 2 cups of beer, and he said, "Okay, there you go. This is for everybody." So why will that be true? And this is something that might be hard to accept because here there is an infinite number of mathematicians. The thing is, they will order some amount of beer, which is half of what the previous person ordered, and yet, even there are infinitely many of them, the bartender said, okay, these 2 beers or these 2 cups of beer would be enough for everybody, right? So basically, that's how infinite series uh, sometimes make no sense because you're summing up an infinitely many number of terms and yet you get a finite sum. And such is an example of a convergent series, right? So just to remind you what the series is, let's go back to that example later. So and then let's prove that the bartender knows his math well. So let's see. Okay, a series is of this form, or an infinite series to be more specific about it, is the summation of some an as n goes from 1 to infinity, right? So basically what we're doing here is we take a1 plus A2 plus A3 and so on until infinity. And we say this is convergent if the sum is finite or if it exists. And when I say exists, it exists as a finite number. And it is divergent otherwise. It is divergent if you cannot decide what the actual sum would be as you carry on the infinite summation, or if it will be infinitely large. For instance, the summation of, say, the summation of k, from k going from 1 to n, from 1 to infinity, is divergent because if you write down the summation, so here I'm drawing up some intuitive arguments just to give you an idea what divergence or convergence means in layman's term. But we'll have some formal tests to verify these conclusions later. So if you look at this summation, we're summing up k's as k goes from 1 to infinity. So when k is 1, you get 1. K is 2, k is 3, k is 4, and you do this infinitely many times, right? So you add up numbers, and you see that if you go to infinity, you will not get a finite sum because you keep on adding numbers that becomes large in the tail end, right? So if you go on with the summation forever, you'll not get a finite answer. So this is divergent. In contrast to this this series, and not I'm completely changing this variable. This is what we call a dummy variable. So it is just the index of the summation, meaning you can change it as long as you're consistent. So that means you replace the n's you see here by integers starting from 1, 2, 3, and so on. Okay. So this one, if you expand the sum, so what would be the first term? The first term is when n is equal to 1. So we'll get negative, So we'll get negative 1 plus when n is 2, we'll get negative 1 quantity squared, which is 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus, and so on. Do you think we will come up with a finite sum here? Or will we get a sum at all? Will the infinite sum exist?
No, it'll be oscillating.
Yeah, you're correct, Daryl. So it would be oscillating because though some students will say, oh, 2 consecutive terms will just cancel out to 0. So negative 1 plus 1 would be 0. The next 2 terms would be 0. The next 2 terms would be 0, and so on. So essentially, if you take them pair by pair, you'll just get a bunch of zeros. When you add a bunch of zeros, it seems that the answer would be 0, right? So this is some kind of ambiguity that we want to avoid in our discussion, because this one actually is divergent by definition, because formally, to remove the ambiguity, right? Because yeah, you can argue, okay, negative 1 plus 1 is 0. Then I'll go to the next pair, negative 1 plus 1, that's 0. And then if I take them by pairs, I'll just get a bunch of zeros, and infinitely many zeros added up will just be equal to 0, right? Now, to avoid that ambiguity, what let's give a more formal definition for convergence. Now, we define the convergence of a series by the convergence of the sequence of partial sums, right? So, which brings me to the sequence of partial sums. How do you get the sequence of partial sums? So you just get the sequence S sub n, where S sub n is the sum of ak, k going from 1 until capital N. So basically, you look at the partial sums. So, for instance, S1, that's the first sum. The sum of the first term is just itself, -1. S2, which is the sum of the first two terms. Oops. -1 plus 1, so that's going to be 0, right? S3 would be the sum of the first three terms, -1 plus 1 minus 1, so that's a -1. Then you can guess S4 is 0, S5 is equal to -1, oops, and so on, right? So basically the sequence of partial sums here is -1, 0, -1, 0, -1, 0, right? And here's our formal definition. So if the sequence of partial sums is convergent, then the series is convergent. Otherwise, it's divergent. So in this case, the sequence of partial sums is this guy. And I hope by now it's clear that this is divergent, right? Because we don't know what will happen towards infinity. Will we go to -1 or will we go to 0? Actually, we won't approach any of those values because they will just keep on oscillating or alternating in the end of the list. So the sequence of partial sums is divergent. So the series is divergent. So this is also divergent. All right. Now, there are some series that are convergent. What would be an easy example? Well, let me add a page here. Still have a minute. Or maybe I'll go to my example here, my introductory example. So if we will write it as an infinite series, right? So the first orders a beer. So that's A1. And then the second mathematician orders half a beer. Third mathematician orders a fourth of a beer. And then I know we can guess that 4 would be 1/3. So basically here, what is the pattern? So it seems that AN is equal to what? 1/2 to the power n minus 1. Because it looks like that half of what the previous mathematician ordered, right? So when n is equal to 1, you get 1, n equals 2, you get 1/2, n equals 3, you get 1/4, and so on. And so the order of the nth mathematician would be 1/2 raised to the n minus 1 cup of beer, right, or glass of beer, right? So if you take the sum of n going from 1 to infinity, so we're taking the sum of 1/2 raised to the power n minus 1, as n goes from 1 to infinity. And this is an example of a geometric series, which we will go back later. Now, a geometric series is of the form summation of a r to the n, as n goes from 0 to infinity. So I need to rewrite this in terms of this form. Okay. Now, the thing here is that the summation should start at 0. Okay. So I need to adjust it a little bit. So here I'll have summation. I want the summation from 0 and go to infinity, right? But since I decreased the index, I need to increase what's on the exponent. So this would be 1/2 to the power n. So that if I go back when n is equal to 1, I'll get, if n is 0, which is the first term, I'll get 1. If n is 1, I'll get 1/2, which is that. 2, I get 1/2 squared, so that's 1/4. That's my third term, and so on. So basically, this is another way of writing the sequence we're interested in. And we will see next time that this is just equal to 1 over 1 minus 1/2, which is 1 over 1/2 equal to 2. The bartender is correct that if the mathematicians will order half of what the previous one ordered, he just needs 2 cups of beer in order to satisfy everyone. All right. So we'll go back to this later together on Monday and look at some more examples about testing whether a series is convergent or not. I'll go back to the concept of looking at the sequence of partial sums because I guess there are some exercises in this worksheet that requires that. And then we'll go to the basic test for divergence and geometric series, such as the problem of the mathematicians here. Okay?
Hey, Neil, I have 2 questions before you go.
Oh, sure. Go ahead. Yeah.
So, for that 4th term right below this picture,
Uh-huh.
why wasn't it 1 over 8?
Yeah, this should be 1 over 8.
Okay. And then my second question was, could you re-explain how you got 2 from the 1/2 to the power of n?
Uh-huh. Oh, okay. How I got this okay. How I
Yes.
got this sum here?
Yes, sir.
Well, there's a theorem about geometric series. If your series is of the form sum of a times r to the n, and
Oh,
going from 0 to infinity, this is equal to a over 1 minus r. So
okay.
again, I'll look at what is a and r. So if I compare these two guys, so here I see that, okay, a should be equal to 1 because that's the constant multiplier in front of the power of n, right? And then what's raised to n? R is the one that is supposed to be raised to n. Here, our base is 1/2, so r is equal to 1/2. So I simply plug in a equals 1, r equals 1/2, and I simplify, I'll get 2.
Okay. Thank you.
Yeah, we'll go back to geometric series next time with some more examples. So I just want to finish off with this sort of introductory example, but we'll see this formula in action later for some more interesting questions. Right?
Thank you, Neil.
Okay, you're welcome. All right, so thank you guys for coming today. So see you again on Monday, and we'll talk about more series. Have a good weekend, everyone.
You too, Neil.
Yep. Thank you.